All right, in this physics journal, we're going to go over the notes on gravitational potential energy. So we're going to start out with our question is, you throw a ball upwards at the peak, where did all its energy go? And the answer, right, the reason that we talk about that is like as the ball goes up higher and higher and higher, it's obviously going to go slow down. It started with kinetic energy, but then as it reached the top, obviously it's going slower and slower and slower. So where did all that kinetic energy go that you originally gave it? Well, the answer is gravitational energy, right? It's gaining gravitational energy. So the next part is right. An object in a gravitational an object in a gravitational field could fall, thus it possesses gravitational potential energy. So, right, if it falls, obviously it's going to gain kinetic energy. That energy has to have come from somewhere. It came from the fact that it originally had gravitational potential energy. Remember that the word potential just means stored energy, and we're going to represent that with an E subscript G, right? E for energy, G subscript G for gravity. So it says consider lifting an object at a constant velocity. And so if you're lifting something, right, you basically need to apply a force that is cancels out gravity. So, right, you're gonna have a downward force of gravity, you're gonna have an upward force of lift, and those two are going to be equal so that the thing moves at a constant velocity upwards. And if we were to make a force versus X graph, where in this case the X is the height, right? How high you lift it, then that graph would be a horizontal line. And the reason that it's going to be a horizontal line is because right, it doesn't matter if you've lifted it 1 meter or 2 meters or 3 meters or 4 meters. The force that you need to apply to that object would be the same to lift something, starting at 1 meter or starting at 3 meters, right? The lift force does not depend on the height of the object, right? In comparison to like springs, right, where when we made a force versus x graph to stretch a spring, at 2 meters takes more force than it does at 1 meter. So meaning that it gets harder and harder and harder to stretch or compress a spring. So it says, recall that the area underneath a force versus x graph represents the energy. So we did that when we made a force versus x graph for the elastic energy, right? We said the area underneath a force versus x graph gives you energy. That is true for any force versus x graph. In this case, the area was a triangle, and so hence the 1/2 base times height. But for this one, the area is going to be a rectangle, right? So not it's just base times height. Where the base, this is kind of confusing, but where the base is right the the base of the which is actually the height, right? Because meaning the physical height that you've lifted the thing, and then the height of the triangle or of the rectangle is the lift force. And so right, your base is the this part is the height, and the height of the rectangle is the lift force. The lift force is equal to mg. Just looking at the force diagram here, you can see that that would be the case. And so basically that gives you this as your equation. Gravitational energy is equal to mgh. So it's typically written as mgh there. Looking at the final notes here, it says always choose h equals 0 to be the lowest point the object reaches. So, it's not necessarily always the ground. It could be the lowest, whatever the lowest point that the object goes, choose that to be h equals 0, and you would measure all your h's, all your heights relative to that point. So, all right, so now let's go ahead and take a look at your example problems here. So the first one, just practice using this equation basically. The first one says, how much gravitational energy do you, 65 kilograms, have at the top of the 160 or 184-meter tall Space Needle? So all we got to do is we got our gravitational energy equation, mgh. Um, Looking for the gravitational energy, Eg, and we just plug in the 65, the 9.8 for G, and the height 184, 184. And then, right, plug that into your calculator, and you're going to get that you have 117,208 joules of gravitational energy. So there you go. B says, how high would you have to lift a 100-kilogram car to possess the same energy? So, right, same deal here, except that the difference here is we know how much gravitational energy that car is going to have. And so we know that it's going to have the same amount of energy as we had up here. So it's going to have 1,100, or sorry, did it again, 117,208 joules of energy. The mass is now 1,000 instead of 65. Still got our 9.8 there. And we're solving for H this time, right? So 1,000 times by 9.8 is going to give you 9,800. And we still have the on that side. Then you're just going to divide both sides by 9,800. And so you're going to get that H is equal to those things divided. 117,208 divided by 900 or 9,800, you're going to get 11.96 meters as the height. So definitely don't have to lift that 1,000-kilogram car nearly as far. So, well, that's it for the gravitational potential energy notes. Hope that you found this useful. Thanks for watching. As always, let me know if you have any questions.